Watch as this spinning cutter tears away solid metal to reveal the precise geometry of an aerospace gear hidden inside the raw block. This is subtractive manufacturing. It is a class of production where we achieve our final engineered geometry by systematically removing material from a larger mass. The process always begins with what engineers call stock, a solid, unshaped block of raw material that is locked into the machine's work area before any cutting begins. Long before the Industrial Revolution, this exact physical logic was executed entirely by hand. A sculptor striking a chisel against a stone block is performing a manual subtractive process. They start with a rough mass and gradually chip away the excess to reach a highly detailed end state. Modern industrial manufacturing scales up this exact same principle. But while a sculptor relies on human muscle, modern machining requires extreme precision and massive mechanical forces to shear through industrial alloys. This chart breaks down the entire machining process. Notice how all material removal strictly divides into two top-level physical categories, traditional and non-traditional machining. The left side of the taxonomy is the domain of physical cutting. This is where physical tools make direct contact with the stock to forcefully carve out shapes. On the right side, we find non-traditional machining. These are advanced techniques like electrical discharge machining, or EDM, which use non-contact erosion instead of physical force. Mastering manufacturing requires understanding this split. You have to know exactly when to rely on the blunt physical force of a cutter and when to use directed energy to sculpt a part. Let's start with traditional machining. By definition, this is the removal of material through direct mechanical shear. The entire process relies on the physical dominance of a cutting tool. The tool must be strong enough to forcefully tear ribbons of material away from the weaker raw stock. Looking back at our taxonomy chart, traditional cutting divides based on the desired geometry. The branch for circular shapes outlines the methods used to create cylindrical parts. Turning, boring, and drilling are the primary operations dedicated entirely to generating these round profiles. These operations are typically performed on a machine called a lathe. In a lathe operation, the raw material rotates continuously at high speeds, while the cutting tool remains firmly stationary. Because the stock is spinning against a fixed point, the tool shears off a continuous ribbon of material, generating a perfectly cylindrical profile along the axis of rotation. Engineers rely on this specific relative motion to machine precise rotational components, like an automotive driveshaft. To create flat surfaces, slots, or prismatic shapes, we invert that kinematic relationship using a milling machine. Here, the workpiece is held rigidly stationary, while a multi-toothed circular cutter rotates and feeds downward into it. Driving a spinning multi-point cutter through fixed stock allows the machine to carve out complex three-dimensional cockets and perfectly flat planes. This is exactly how the intricate internal cavities and mating surfaces of a cast engine block are hollowed out and refined. To breach the gap between this bulk material removal and final finishing, we use grinding machines. Grinding uses high-speed abrasive wheels packed with microscopic cutting edges to strip away minute amounts of material. Whether you are spinning the raw stock on a lathe or spinning the cutter on a mill, traditional machining is always an act of aggressive, highly controlled physical tearing. The massive physical forces required to shear solid metal generate extreme volatility. Without specialized support systems, those forces would instantly destroy the unequipped machine. First, the machine requires work-holding devices. These components rigidly secure the raw stock, preventing the aggressive lateral forces of the cutter from ripping the part out of the work area. Lathes typically use chucks with tightening jaws to grip rotating cylinders, while milling machines rely on heavy-duty vices or custom-bolted fixtures to lock down stationary blocks. On the other side of the cut, cutter-holding devices like collets and arbors are needed to lock the cutting tool to the machine's spindle with absolute concentricity, ensuring it spins perfectly on its axis. Then there is a strict material science constraint. The cutting tool must possess a significantly higher hardness scale than the workpiece. If it doesn't, the tool will immediately deform upon impact. Watch what happens with an inadequate hardness differential. A standard steel tool blunts and deforms against a hard titanium workpiece, but a rigid tungsten carbide tool successfully shears that exact same titanium. To maintain that dominance, modern manufacturing relies on highly engineered cutter materials, specifically high-speed steel, tungsten carbide, and industrial ceramics. Tearing metal apart creates immense thermal buildup at the shear zone. We flood this area with cutting fluids, which act as a coolant to rapidly dissipate the extreme heat before it can warp the part or melt the tool. These cutting fluids serve a vital secondary function. They provide constant lubrication to reduce friction between the tool and the stock, minimizing tool wear over time. Traditional machining is practically impossible in isolation. It requires a perfectly synchronized ecosystem of rigid holders, super hard materials, and fluid dynamics just to remain stable during the cut. But physical shear always has strict limits. When aerospace alloys are simply too hard for a physical cutter, or the required geometries are too intricate for a spinning tool to reach, traditional machining fails. This is where we cross over to the right side of our taxonomy map. Non-traditional machining. Non-traditional machining is the utilization of localized thermal, electrical, or kinetic energy to erode material without any direct mechanical contact between a tool and the part. The most common method is electric discharge machining, or EDM. EDM uses controlled electric sparks submerged in a dielectric fluid to selectively melt and vaporize the metal. Zooming in, you can see the absolute lack of mechanical contact. A microscopic, high-voltage spark jumps across the fluid gap to instantly vaporize a tiny crater into the surface. Because no physical force is applied, EDM is ideal for cutting highly intricate dies out of hardened tool steel without risking deformation. Another major thermal method is laser beam machining, or LBM. This process focuses a high-intensity beam of coherent light to rapidly melt or ablate complex profiles, most often used on flat sheet metal. For materials that cannot survive extreme heat, engineers use water jet machining. This method fires a hypervelocity stream of water mixed with abrasives to cleanly and precisely slice through heat-sensitive targets. Finally, ultrasonic machining handles highly brittle materials like glass. A tool vibrating at extreme frequencies drives an abrasive slurry against the surface, gently chipping away the profile at a microscopic scale. When an alloy is too tough to cut, non-traditional methods bypass the physical limits of hardness and tool wear by weaponizing energy itself to erode the stock. Even after the most precise traditional or non-traditional machining, the newly exposed surface is still flawed. At the microscopic level, the metal is a jagged landscape of peaks and valleys. To resolve this, we apply super finishing processes. The goal here is not to alter the bulk geometry of the part, but strictly to improve its microsurface integrity. One primary method is lapping. This involves trapping a loose abrasive slurry between the workpiece and a softer lapping tool. The friction slowly wears down those microscopic high points until the surface achieves extreme optical flatness. Lapping flattens, but polishing smooths. Polishing utilizes fine abrasives mounted on flexible backing wheels to buff out microscratches and achieve a specular, mirror-like finish. For internal geometry, like engine cylinders, we use honing. Honing relies on rotating, reciprocating abrasive stones to true up the cylinder and create a precise crosshatch pattern on the walls, a texture specifically designed for oil retention. This is the complete subtractive journey. It traces a path from the violent bulk removal of a milling cutter tearing through raw steel, all the way down to the microscopic leveling of a lapping plate. From bulk removal to superfinishing, this highly controlled, multi-stage destruction of raw stock turns simple mass into perfectly functional geometry.
Namaste. Thank you so much for watching. If you found this helpful, don't forget to like, share, and subscribe for more knowledge and keep learning.